Newton's third law. Chapter is Dynamics and the topic is Newton's third law. Definition. Every action has reaction equal in magnitude opposite in direction but kind of forces, mean forces of action reaction, is same. Now there are only two kinds of the forces. One is the balanced forces and number two is unbalanced forces. So I repeat, every action has reaction equal in magnitude, opposite in direction, but the kind of the forces is same. Mean the kind mean balanced, unbalanced. So force of the action is exactly equal to the force of reaction, equal in magnitude, but opposite in direction. And the next, both forces, action and reaction, are acting at two different objects. Mean if action is at A, then the reaction will be at B. And the time of the action exactly the same time of reaction. Mean both will occur in the same interval of time. And the very important, their kind is same. If the action force is balanced, definitely the reaction force will be balanced. When action force is unbalanced, reaction will be unbalanced in its nature, in its kind. Okay, this is the formula for both kinds, balanced and unbalanced. But if it's confirmed that the both forces are unbalanced, then according to Newton's second law, every unbalanced force is equal to change in momentum over time. Mean the rate of change of momentum is equal to an unbalanced force. So we can replace these forces. Change of momentum over time of A is equal to minus change in momentum over time of B. This is only situation when the forces are unbalanced. Now, both times are equal, so we can cancel them. Then the shape will be change of momentum of A is equal to minus change of momentum of B. So this is another form of the formula for the Newton's third law. For example, two objects. This is A, this is B. Both are moving towards each other. Its momentum suppose 7 Newton second and its momentum suppose 5 Newton second. If this direction is taken positive, then this will be taken negative. When we will draw the graph, against momentum, Newton second, and time, then the object A has momentum this, which is 7 suppose. And the object B has momentum this minus 5. So this is the initial momentum of A. This is the initial momentum of B. Now, suppose this is the time at which both collide with each other, and this is the position of the collision. After collision, if the object A is moving in this direction with momentum suppose 3 Newton second, but due to the left side direction, we will consider it's negative. So after collision, the momentum of the A changes and it becomes minus 3. Suppose this is minus 3. And this is suppose the time, mean the time when the momentum or the collision ends. This is the end of the collision. So this gap is the duration of the collision. So what is the change of the momentum of A? This is the final momentum of A. So the change of momentum of A is 7 minus 3. It means the total momentum change is 10. Now, according to Newton's third law, change of momentum of A is exactly change of momentum of the B during collision, during action reaction, but opposite in direction. So initial momentum of minus 5, initial momentum of B is minus 5. So definitely its change of momentum is also 10. Yes, for this B is moving in the opposite direction than with momentum 5. So this object B is going back with 5 Newton per second because according to law of this Newton's third law, change of momentum of A is equal to change of momentum of B in magnitude. So the 10 for A, so the 10 for B. So this is the graph for the change of momentum for both A and B. Now, according to this formula, change of momentum divided by time mean the gradient of momentum time graph is the force. Now, the gradient of this line is negative. Gradient of this line is positive. Both gradients are equal. They are equal to force, but they are opposite in direction. So if this line is representing the action, then this line will be representing reaction. Both are equal in magnitude, but one positive, other negative. So we can calculate the force of action and the force of reaction and their direction. So this is the graph for the change of momentum. Now, change of the momentum of A is exactly equal to the change of momentum of B. So we can write m change of velocity of A is equal to minus m change of velocity of B because momentum is mass into velocity. So change of momentum mass into change of velocity. So we can write here final momentum minus initial momentum of A is equal to minus time final momentum of B minus initial momentum of B. Then MA VA minus MA UA, this minus MB VB, and minus plus MB UB. Now rearrange them. MA VA plus MB VB is equal to MA UA plus MB UB. So this is the final shape of the equation. Look, final velocity of A, final velocity of B. So this is the total final momentum. Total final momentum mean after collision, total momentum of both. This is U, this is U. So this is the total initial momentum before collision. So we can write total momentum before collision is exactly equal to total momentum after collision in an isolated or closed system. Do remember, isolated closed system mean only two objects are interacting with each other. No third body is involved. So this system is isolated, this system is closed. So the total momentum before collision is equal to total momentum after collision. This statement is called law of conservation of momentum. So the Newton's third law, we started it from Newton's third law. Look, this is the Newton's third law, and this is the final shape. So Newton's third law is also the law of conservation of momentum. Now, important, change of momentum is force into time. Change of momentum is m times delta v, and the change of momentum can be written as m final velocity minus initial velocity. So when we will write change of momentum of A is equal to minus change of momentum of B for the Newton's third law, and we can also write FATA minus FBTB. So this is another shape of this change of momentum. Okay, next, suppose this is the object and it's moving in this direction with suppose 7 meter per second velocity. And another object is stationary at its path. Initial velocity is 0, mean it is at rest. This is a situation number 1. Number 2, this object is moving 7 meter per second, and this object is moving now with 2 meter per second. Third situation, this object is moving with velocity 7 meter per second, and the second object is moving in the opposite direction, suppose with 2 meter per second. So these are the three types of the collisions. Now in number 1, this moving object will collide in the stationary object. In second, this object will collide with the second while overtaking it. And the third is head-on collision. Now, according to our knowledge, our experience, the intensity of the collision will be maximum in this, and minimum in this, and the medium in this. But in physics, we have to calculate this intensity of collision. So definitely head-on collision, this third one will be the strongest among three. But we have to calculate this. Now, to calculate the intensity of the collision, we have to calculate relative velocity of approach towards collision. And it is calculated by u1 minus u2. U's are the initial velocities, not speeds. velocities before collision, and velocity is a vector. We have to consider the direction. Now, for the first, we calculate u1 minus u2. This is number one object. This is number two. So u1 is 7 and the u2 is 0. So the answer is 7 meter per second for the first one. Now move to the next one. u1 minus u2. The u1 is 7 and this is 2. So answer is 5. Now the third one, u1 minus u2. u1 is 7 minus, and this is towards left. So we will write it minus 2. So the answer is 9. So look, 9, 7, 5. So the relative velocity of approach is maximum for this head-on collision. So we can write that intensity of collision is proportional to u1 minus u2. If the intensity is maximum, mean the relative velocity of approach towards collision is maximum. If intensity is minimum, then the relative velocity of approach is also minimum. So intensity of the collision depends on the relative velocity of approach towards collision, which is u1 minus u2. Now, there is another Newton's law, which is called Newton's law of restitution. Statement is, in a perfect elastic collision, in a perfect elastic collision, relative velocity of separation after collision is equal in magnitude but opposite in direction to the relative velocity of approach towards collision. In a perfectly elastic collision, this is the name of, this is a type of the collision, one of the type. Relative velocity of separation after collision is equal in magnitude but opposite in direction to the relative velocity of separation, the relative velocity of approach. Now, the relative velocity of approach is u1 minus u2. And the relative velocity of separation will be similarly v1 minus v2. And according to the statement, relative velocity of separation is equal in magnitude but opposite in direction to the relative velocity of approach. But the type of the collision must be perfectly elastic. Mean we can write v1 minus v2 is equal to minus u1 minus u2. So this is the formula. If the velocity of separation is equal in magnitude but opposite in direction to the velocity of separation, then the collision is perfectly elastic. Otherwise, it is inelastic. So we have to study two types of the collision, one elastic, other inelastic. If this equation is valid, we will write it's elastic. If this equation is not valid, we will write inelastic. For example, This is the object. It's moving in this direction with 5 meter per second. This is the object. It's moving in this direction with 2 meter per second. And after collision, this object A is moving in this direction with 3 meter per second. And this object B is moving back here with velocity suppose 1.5 meter per second. Now we have to check whether the collision is elastic or inelastic. We will calculate their relative velocity of approach and relative velocity of separation. So this is approach. So u1 minus u2. So 5 minus 2, it becomes 7. This is the velocity of approach. And here is the velocity of separation, v1 minus v2. Look, this is v1. This side, left side, just become minus 3, minus, and this is 1.5. So it is 4.5 meter per second. Both answers are not equal. So this is inelastic collision. It's not perfectly elastic. If the velocity of separation is equal to the velocity of approach in magnitude, opposite in direction, then the collision is called elastic, mean the perfect elastic. If they are not equal, then the name of the collision is inelastic. Okay, Newton's third law, FA is equal to minus FB, or the law of conservation of momentum, MAUA plus MBUB is equal to MAVA plus MBVB. Both are valid for elastic and inelastic. So from the Newton's third law and from the law of conservation of momentum, we can't distinguish between the types of the collision, whether it's elastic or inelastic. Mean both are equally valid for both elastic and inelastic. And this is the single equation which will give you the separation or identification of the elastic or inelastic. It can be written as V1 minus V2 over u1 minus u2 is equal to minus 1. If the ratio of the velocity of separation, ratio of velocity of approach is coming 1 or minus 1, then this will be elastic, mean perfect elastic. If this ratio is not coming 1, then it will be inelastic. Now suppose after collision, two objects are not separated from each other. Then the velocity of separation v1 minus v2 will be 0. After collision, they are not separated, they are entangled, they are fixed with each other. So their velocity of separation is 0. So which is the proof that v1 is equal to v2, mean both are moving with the same velocity. So it is confirmed that if the objects are not separated, then the collision will be inelastic. If they are separated, then we will apply the equation whether the answer is coming minus 1 or not. Okay. Now elastic, comparison between elastic and inelastic. First, second, both obey law of conservation of momentum. Number 2, both obey law of conservation of energy. Mean total energy before collision is equal to total energy after collision. So these are the two similarities. Now the difference. In perfectly elastic collision, kinetic energy total before collision exactly equal to the kinetic energy after collision. Mean kinetic energy in elastic collision is conserved. But for inelastic, kinetic energy before collision is not equal to total kinetic energy after collision. Mean it is not conserved. If kinetic energy is conserved during the collision, that is perfectly elastic. If kinetic energy is not conserved before answer and after answer different, then it is inelastic. This is the first difference. And the next difference is we have done the velocity of separation and velocity of approach ratio is 1 minus 1 exactly. But here, V1 minus V2, U1 minus U2, this ratio is not 1 or the minus 1. It will be different. So these are the two similarities, and these are the two differences between elastic and inelastic. Now, if the objects are identical, there are few observations. This object, this object, this object is at rest. This is moving with certain speed, a certain velocity v. When this object will collide with its stationary object, the object A becomes stationary at the same position, and the object B will start motion with the same velocity v. So the stationary becomes moving, and the moving becomes stationary, and the stationary will carry the same velocity from this A. And number two, if two objects are identical, one is moving with velocity 7 meter per second, other moving with 2 meter per second. When they will collide, this is A, this is B, both will change their direction and they will exchange their velocity. So this is moving with 2 meter per second. This will be moving with 7. So A and B. And here, this is moving, suppose, with 7. It is stationary. Then the stationary will start moving with 7 and the A becomes stationary. And this is only possible when the collision is perfectly elastic. These are the observations for the perfectly elastic collision. Stationary starts motion and the moving becomes stationary. If they are moving towards each other, head-on collision, perfectly elastic, they will exchange their velocities.